All right, y'all. Welcome back from Thanksgiving holiday. I hope everyone had an enjoyable turkey day with the family and you didn't have to think about any math whatsoever. But alas, you are back and you must continue to learn math. However, the good news is that we are in the home stretch. I think we only have 2 more lecture weeks and then finals week. So my plan is to button up chapter 11 this week, and next week will be a review week where we'll go over all the most salient material from the semester in preparation for the comprehensive final exam. So let's get to it. So we were talking about logic. That's chapter 11. And we left off last lecture with the implication. So we went over all of the nitty gritty about logical implication. And so now we are going to continue on that road and also add in some additional concepts of equivalence and what your book is making distinction here between just regular old implication and logical implication, which will make more sense by the end of this lecture. Okay, so let's jump right in. Definition: two statements, think P and Q, are logically equivalent if their truth tables are identical. If their truth tables are identical. So what does that mean? So suppose we wanted to look at the statement P implies Q, and I am going to, in anticipation of this section, replace that symbol with that symbol, and I will expound upon that further later in this lecture. So we want to see is P, we want to compare and contrast the truth values of P implies Q with not P or Q. So we draw up a truth table, and then we look at the outcomes for the two different statements. And what we discover is that whenever P implies Q is true, so is not P or Q. And then whenever P implies Q is false, so is not P or Q. So notice that the truth values all came out the same for the same assignments of truth values for the variables P and Q. So when this happens, when they're identical in this sense, we say that the two statements are logically equivalent. Okay, so I'm going to undo this symbol. I'll make more sense of that in a second. So logical equivalence is represented by this symbol here, which I've been using as the biconditional symbol, but your book is using slightly different notation than I'm used to. So they're going to use this to indicate logical equivalence. So these two statements are logically equivalent when we put this symbol between them, or that means the same thing. Okay. And logical equivalence, remember, means the truth values come out the same. So let's look at an example. We have two statements here. Not P implies not Q, and Q implies P. We want to show that these two things are logically equivalent. So when we put that symbol there, we're saying this, whenever this is true, so is this, and whenever this is false, so is this. So let's see if that's true. So we build our truth table, P and Q. We're going to have 4 rows because we have 2 variables. 2 to the 2 is 4. So we do true, true, false, false for P, then true, false, true, false for Q. And then we're going to look at, I'll build it up in pieces. Not P implies not Q. And we're going to look at Q implies P. And we're going to use the little shortcut that the book uses by essentially imagining a invisible column here for the connective implication symbol so that we don't have to write extra columns. Okay, so let's do it. Whenever P is true, not P is false. Okay, so true, true means false, false for not P. And then when P is false, not P is true. Okay, so we do the same thing for not Q, and we end up with false, false, true, true. And all we're doing is flipping around those truth values there. And then we use this imaginary column here to stand in place for the full statement, not P implies not Q, but we just put it under the implication symbol. Oh, excuse me. So we just got to remember our rules for implications. And remember, I think in terms of fact, fiction, this keeps it straight for me. So in a work of fiction, is it okay to have fiction? Yes. In a work of fiction, is it okay to have fact? Yes. In a work of fact, is it okay to have fiction? No. In a work of fact, is it okay to have fact? Yes. Okay, now we're going to look at this column. And here we have Q and P, which we already have the values for here, so we don't really need to fill them in here, but we could if we wanted to. So that was true, true, false, false. And then this one was true, true, false, false. So we go through the same analysis here. In a work of fact, is it okay to have fact? Yes. In fiction, is it okay to have fact? Yes. In a work of fact, is it okay to have fiction? No. In a work of fiction, is it okay to have fiction? Yes. So once we go through this, all we're interested in is the comparison of this column and this column. And what we see is that the values in this column are identical to the values in this column. And what that means is that these two statements are logically equivalent. So they're essentially the same statement, just with different symbols. That's what logical equivalence means. So these two examples are actually special examples. The example up here, P implies Q is logically equivalent to not P or Q. This we'll find very useful later in this section when we're trying to simplify more complex statements involving implications. And this statement here, not P implies not Q, is the same as Q implies P. We'll learn it's called the contrapositive. So it's another special kind of statement. So some important notes here. What does logical equivalence mean? Really? We say two statements, P and Q, are logically equivalent if the biconditional of P and Q is a tautology. Okay, meaning whenever P is true, so is Q. And whenever P is false, so is Q. Okay, so that's what it would mean to have a tautology. And the important point to be made here is that we have two different symbols. We've got the double arrow, the arrow pointing two different directions here, the bidirectional arrow, and then we have the double bidirectional arrow. Now, this is a notational issue and one where I haven't been following the conventions that the book has been following, and this is going to lead to some confusion at this point. So I need to stress this because this is not something I was used to. And so I've been inconsistent with my notation, but I'll try to be better going forward. So these are not equal symbols. This does not equal that. The only time that these are equivalent is when the statement that the biconditional arrow is applying to is a tautology. So there's no reason that this has to be a tautology. And if it fails to be a tautology, then we cannot substitute this symbol. So the idea is this: if this is a tautology, meaning it's always true no matter what the values of the variables are, then we can make the more profound statement that P is logically equivalent to Q. So these are not the same. Putting this here means we know that the biconditional is a tautology. Okay, so I will be better about using this notation the way that the book wants to use it. However, I will say that this is not a universal convention, not one that I had ever been exposed to. You know, when I was learning about logical equivalence, we didn't necessarily use this symbol at all. We just used an equal sign. P equals Q means they're logically equivalent. But your book wants to use the double arrows, so we will go from there. Okay. So as I stated before, we have a special statement, which we call the contrapositive. And we saw that this was a logical equivalence. And that contrapositive says this, that P implies Q is logically equivalent to not Q implies not P. Okay, so notice what's happened here. I take P implies Q, I flip it over to Q implies P, but then I negate the two variables. When I do that, I form the contrapositive statement. So let me say this more clearly. This statement is the contrapositive of P implies Q. Okay, so whenever you're given some implication statement, you can always form the contrapositive by flipping the variables around and negating them. The claim is that this is logically equivalent. So we'll go over that. But first, let's look at, or we just proved that actually. At the beginning, we showed that not P implies not Q is the same as Q implies P. This was the contrapositive. So we showed that the contrapositive formed identical truth table to the implication, and therefore they are logically equivalent. So we already know they're logically equivalent. Let's see what this looks like just in plain old English. So suppose we have the statement, I am dirty for P, and Q is the statement, I take a shower. Okay, so we have the very simple statement, P implies Q. If I'm dirty, then I take a shower, obviously. But this is logically equivalent to the statement, not P implies not Q, which we would read, if I haven't taken a shower, then I was not dirty. Seems obvious. But notice that we've flipped the order around. So now the shower statement comes first, but we negate it. And then the dirty statement comes second, but we negate it. So that's what the contrapositive looks like in plain old English. Okay. Now there's a quicker way to, well, let me just go back to this real quick and just say, contrapositive, we know how it's formed by negating the two variables and flipping them around in the implication. We know how to translate it into English. And though we didn't know it at the time, at the very beginning of the lecture, we proved that the contrapositive is a logical equivalence. So we can move on from the contrapositive. You've seen it, you understand it. And one thing I will stress here is that for you right now, it might seem like this is just a factoid, not necessarily useful in any particular way. But I can tell you as a mathematician that there are times when you're trying to show that two things imply one another, but you can't show it directly. for whatever reason, it's just too difficult to show that this is true. But if you try to show the contrapositive, it's easier, and there's a clearer path to actually showing that this statement is true. So the contrapositive is useful because sometimes it's easier to show the contrapositive is true than to show that the direct statement is true. So that's why we go over it. All right. So in this section, we also learn about De Morgan's laws. Now, we've seen De Morgan's laws before, if you remember, back in the chapter where we were learning about sets. I think that was chapter 5. So we learned about De Morgan's laws in chapter 5, and most of you did pretty dang well with De Morgan's laws. You understood how they worked and were able to apply them. So we'll go over that in a second, but here's just the simple statement. So what are De Morgan's laws in the logical context? If we have a statement like P or Q and we negate it, then the negation of P or Q is logically equivalent to this the statement not P and not Q. Conversely, we could negate the statement P and Q as opposed to P or Q, and this is logically equivalent to not P or not Q. Okay, so there's something very simple at play in these laws, and we'll see it with the example. And once you see it, you'll realize it's just like what we did with the sets, and you probably won't have much trouble with it. So let's see an application of De Morgan's laws. So we're going to use De Morgan's laws to negate the statement P and Q, parentheses, and R. Okay, so let's see how that works. So we're negating the statement P and Q and R. So just like we did with the sets, what we're going to do is, So just like what we did with the sets, what we're going to do is think about distributing this negation symbol. So I'm going to distribute it to the statement with parentheses, and then I'm going to distribute it to the and symbol, and then I'm going to distribute it to the R as well. And so what's that going to do? That's going to negate the statement P or Q. It's going to flip the and statement into an or statement. Excuse me. And then it's going to negate R. So you see, the most important thing to notice is that when that negation symbol hits the and symbol, it flips it over into an or statement. This is just like what we did with sets when you had intersections and unions. And really, intersections and unions are logically equivalent to and statements and or statements. You even remember when we were looking at English sentences and translating them into set language, whenever we saw an and, we used an intersection. Whenever we saw an or, we used a union. So there really is a direct correspondence here. So important, when the negation hits the and, it flips it into an or. Okay, now we're still having to do some work here because we have to now distribute that negation to all the pieces in that parentheses. And so what does that do? It negates the P, it flips the and into an or, and it negates the Q. And then we already had or not R on the outside. So this is the full expanded statement. We see that there's a logical equivalence between negating the statement P and Q and R with not P or not Q or not R. All right. So let's look at another type of problem, not directly related to De Morgan's laws, but related to what we looked at the very beginning of this section. So they're asking us to eliminate the implication symbol and simplify the statement, not P and not Q implies not Q. Okay, so there will be some De Morgan's laws here, but first we need to look back at what we did at the very beginning. And we showed this truth table formed a logical equivalence between the statement P implies Q and not P or Q. So these two statements are logically equivalent. And so we can use this trick to eliminate the implication symbol. So instead of having an implication, we'll negate the first variable and replace the implication with an or symbol. All right. So let's see what that looks like. Excuse me. So the important thing here is to see this in big pieces. This is a big implication statement. This thing implies this thing. Don't worry about all the specifics. This implies that. Now, if we want to eliminate the implication symbol, what do? We negate the first thing, then replace the implication with an or. So we negate the first part, the premise, which is this whole complex statement. And then we replace the implication symbol with an or. So that first step, we eliminated the implication symbol by negating the first part and then replacing the implication with an or. Now we need to simplify, and here we'll use De Morgan's laws. So we now distribute this negation to everything in the parentheses. And when we do that, we negate not P. So not P gives us just P. Negation of and gives us or. Negation of not Q gives us Q. So that clears all that up. And then we still had or not Q. Okay. Now, technically, we can simplify this further, because I can look at this statement. I can now apply an arbitrary set of parentheses and just look at the statement Q or not Q. Now, this will be an exercise, something that you'll have to show for yourself, but Q or not Q as a statement is what we call a tautology. It's always true. It's never false. Because remember, in order for an or statement to be true, you only need one of the variables to be true. But because the two variables are Q and not Q, whenever one of them is false, the other one is true. So there's no circumstance where they are both false at the same time. It's impossible. And since they both cannot be false at the same time, this statement is a tautology. So it's always true. Always true. And when it's always true, it basically doesn't matter. It doesn't change anything. It's just making this ugly. So it can be shown that this part of the statement can just go away. It doesn't change anything. It's a tautology. Q or not Q is always true. So the truth value of this whole complex statement only depends upon P. Whenever P is false, the statement will still be true. So actually, let me think about this for a second. This is always true And P, no matter what the value of P is, you know what, we're just going to, I was trying to do something tricky here, but you know what, I'm just going to probably confuse you some more. So we'll just leave it at this. P or Q or not Q. Yes. I think that is fine. So here we've eliminated the implication symbol and we used De Morgan's laws to expand out the expression. There may be more simplification here, but you got to be careful. There is a tautology here, but then we can't just eliminate this because P can be false. And if P is false, this whole statement's still true. Because if we look at it, it's P or this thing that's always true, P or true, P or tautology. So no matter what P is, this whole thing is always true because an or statement just needs a true. And this thing is always true. So we have to be careful here, but we can leave it at this point. This is us eliminating the implication symbol and using De Morgan's laws to break up the parentheses. Okay. So there's one last little glitch in the matrix here, and it goes back to the book's adoption of this new convention with these arrow symbols that is not something that I was raised in mathematics to know or do in this particular way. So I just need to stress it so that there's no confusion. So definition, we say P and Q are logic. We say P logically implies Q, which we denote with the symbol P double arrow Q, whenever P implies Q is a tautology. So this is just like what we saw with the biconditional. These two things are not the same symbol. This only can be used when we know that P implies Q is a tautology. So we have to be careful with those symbols. But it's really just a variation on the theme that we saw before, which was that the biconditional is not equal to this. These two symbols are not equivalent, and we also can do that for the straight up unidirectional conditional as opposed to the bidirectional conditional. Same idea. Okay, so let's just do one application problem with the logical implication. We want to verify this implication statement. And it turns out we call this the disjunctive syllogism. Okay, so this is tricky, but what we see is that all of this complicated statement with P's and Q's ultimately just depends upon P. So let's see what that looks like. So in order to verify this statement, we need to construct a truth table. So we've got P's and Q's. So we're going to need 4 rows. True, true, false, false, true, false, true, false. All right. And we're going to build up the statement. So let's see, we've got a P or Q. So we can do that as its own column. We have a not Q. And then we have a P or Q and not Q. So we put it all together. So what we should end up with, if this is true, is that we have a tautology, right? So we need P implies Q, which would be this implies that, to always be true. So at the end, we need to take all of this, which I don't really have a lot of room. Actually, what I'll do is use the trick. So this statement implies P. And we'll do the little imaginary column for the implication symbol there, like we've done in the past. All right, let's do it. P or Q. So P or Q is true as long as one or the other is true. We just need one true. So it's only false when they're both false. So all we can see there's only one case where they're both false. Otherwise, everything is true. All right. Not Q just has the opposite truth assignments as Q. So we would have true and true, false and false. Okay. Now we're going to evaluate this big complex statement, this and that. So it's an and statement for these two pieces. So and statements are always false as long as there's one false, and only true when there's two trues. So if we look everywhere there's a false, we know the big and statement will be false. So there's one false there, and one false there, and two trues here. So that big and statement will be true. Okay. Now we're just going to see what happens with this big implication. Now we've got this whole statement, which we have its truth values for, implies P. P we have way over here, but we can write it in here just to make it more convenient. So we can see the values. And then we're just going to evaluate the implication. So this implies that. Fiction. Is it okay in a work of fiction? Is it okay to have fact? Yes. In a work of fact, is it okay to have fact? Yes. In a work of fiction, is it okay to have fiction? Yes. In a work of fiction, is it okay to have fiction? Yes. So this last column is what we're interested in. And we see that we ended up with all trues, no matter what the assignments of P and Q were. And so this means this implication is a tautology. In other words, this whole complex statement, its truth value only depends really on the value of P in a way. Okay, so that's the disjunctive syllogism, and that's how logical implication works. So look, the symbol is just a simple arrow. Once that simple arrow gives us a tautology, then we can replace it with a big double arrow, which tells us that this is a logical implication and not just a simple implication. All right, that's 11.4. I will be following up on Wednesday with 11.5, and I think that might conclude chapter 11 for us. There should be a quiz this week on chapter 11, so brace yourselves for that. And there will be homework, of course, and all that happy stuff. All right.